For decades, engineers have dreamed about launching spacecraft without the need for massive rockets, using tracks, magnets, even giant spinning arms to fling payloads into orbit. It's an idea that's been tested, crunched through the math, and usually written off as impractical or too expensive. Even some of the smartest voices in the space community, including other creators who I hugely respect, have recently laid out why they think this kind of system just doesn't add up. And for the concepts they analysed, they weren't wrong. The physics was solid and the obstacles were real. But here's the thing, the tech those conclusions were based on is not the latest tech being proposed by experts in the field today. A new system called the variable pitch screw launch has quietly changed the rules. Now, it doesn't just make those obstacles smaller or more manageable, it basically sidesteps them entirely. Now, for space access and interplanetary travel, this is a really big deal. My name's Brad, you're watching Hello from Space, and today we're going to be talking about possibly one of the most legitimately revolutionary proposed methods of delivering payload, including humans, to space without using rockets. The variable pitch screw launch system. Now to start, we're going to talk about what mass drivers are, how they work, how they're different to rockets, and why they've historically not been viewed as practical. Now, then we're going to talk about the variable pitch screw launch, or VPSL for short, what it is and how it solves these issues. We're also going to have Phil Swan of the Atlantis Project on to talk about the VPSL system, which he proposed in his paper, Human-Rated Launch Infrastructure for the Interplanetary Era, Breaking Rocket and Legacy EML Cost Barriers. Now, if you're not a scientist or an engineer, don't worry, neither am I. So I'm going to try to break it down in a way that works for both experts and regular people like me, so everyone can follow along. Now, before we dive into this new technology, let's rewind a little bit, because if we're going to understand just how big of a deal this is, we need to first understand why so many smart people, engineers, scientists, and yes, YouTubers, have been skeptical. Now, to do that, we need to talk about one of the more tempting rocket replacement ideas, mass drivers. Now, you've possibly seen it before in sci-fi movies or concept art. A long track stretching up the side of a mountain or buried underground, maybe even floating high in the sky. Now, at one end sits a spacecraft, and at the other end, an exit into the upper atmosphere. Instead of launching by blasting enormous amounts of rocket fuel right from the pad, you accelerate along this track using magnets, rails, or some other ground-based system, then release, letting what would be the upper stage in a conventional rocket finish the trip to space with a lot less work to do. This idea is essentially a super high-tech version of a Hot Wheels ramp. But instead of flinging Hot Wheels into the drywall, you're flinging them into space. Now, in all seriousness, this idea sounds great. It would mean smaller rockets, less fuel, a higher launch cadence, and far lower costs to get into space. In practice, the numbers get really ugly really fast. Now, if you've watched Tim Dodds from the Everyday Astronaut channel's recent breakdown on this, or Felix on the What About It channel's video, you'll know exactly what I'm talking about. Now, you start running the calculations for something like a Falcon 9, and suddenly you're talking about energy demands the size of a small city and entire farms of capacitors, all just to gain a few % more payload capacity. This is why for decades, launch assist has been one of those ideas that space fans like to bring up, and engineers frustratingly explain why it's just not worth the trouble. Now, the first big hurdle is power. Now, accelerating even a modest rocket to orbital speeds in seconds means delivering energy requirements equivalent to multiple nuclear power plants all at once. Now, handling that kind of instantaneous power is an engineering nightmare. Next is complexity. Now, you'd be building a multi-kilometre precision track that can withstand enormous G-forces, and in some concepts, survive a rocket exhaust, or else figure out ignition at high altitude, neither of which is easy. Now, if your engine fails to light, you've pretty much just fired a giant fuel-filled bomb into the atmosphere on a ballistic trajectory to who knows where. And then there's the diminishing returns. Now, traditional electromagnetic launchers like railguns, coil guns, and linear motors have costs that scale with the cube of velocity. Now, double your launch speed and your costs don't just double, they increase eightfold. And by the time you aim for true orbital or interplanetary transfer velocity, the budget has spiraled out of control. Now, this is why engineers and space communicators like Tim Dodd and Felix have been skeptical, and they've been absolutely correct up to now. Now, the physics mostly checks out, but the economics absolutely does not. You might spend billions to gain an extra 3% payload to orbit when a slightly bigger rocket could do the same job for a lot less. At least that's how it's been, because the problem isn't the concept of ground-based launch assist, it's how we've been trying to do it. Now, change the method and those brutal scaling costs and power demands can become far more reasonable, even preferable to traditional rockets. Now, this is where the variable pitch screw launch comes in. Here's where we flip the script. Now, the biggest killer of traditional electromagnetic launch ideas isn't that they can't work, it's that they've all been built around one very specific approach. Convert massive amounts of electrical energy into kinetic energy on the fly. Now, at slow speeds, this isn't scary. Now, accelerating 1 kilogram from 0 to 1 meter a second only takes about half a joule of energy, about the same as a 0.5 watt LED burning for 1 second. But if you want to nudge that same kilogram from 7,999 meters a second to 8,000 meters a second, suddenly you need 8,000 joules. That's 16,000 times the energy for 1 additional meter a second. Now let's put some numbers on it. If we assume an acceleration of 80 meters per second squared, the power needed for that first meter per second is just 40 watts, basically a household light bulb. But for that last meter per second near orbital velocity, the power jumps up to 640,000 watts. That's the output of a small power plant, just to give it that one final tiny push. So what does all that actually mean? Basically, it's easy and cheap to get something moving when it's slow, but the closer you get to orbital speeds, the hungrier every little bit of acceleration becomes. Now, rockets like Falcon 9 actually burn through way more power per kilo than this. At the first stage of Falcon 9 chews through about 1.9 million watts per kilo, and even the upper stage is still at around 187,000 watts per kilo. The raw power needed at orbital speeds is absolutely enormous. Now, rockets do it, but they just brute force their way through a giant controlled explosion. Now, the real issue for traditional mass drivers is that there are thousands of individual segments in a launcher, and each segment is an electric machine that needs to be designed to handle the instantaneous power requirements associated with accelerating the spacecraft through that segment. Now, the faster you want to go, the more segments you need, and the more power each following segment needs to be designed to handle. Now, this is because as the spacecraft speeds up, it's traveling through each segment faster and faster, giving each segment less and less time to impart energy into it. This means each of those segments needs to be progressively more powerful to get the craft up to the required speeds. Now, this is what is sometimes referred to in the industry as the switching problem. Now, the variable pitch screw launch system, or VPSL, instead says, why are we trying to do all the energy conversion on the fly? What if we converted electrical energy to kinetic energy gradually in advance, and then when we're ready to launch, we're only transferring that stored kinetic energy to the spacecraft on the fly? Now, instead of a railgun or coil gun pumping massive electrical pulses down the track, VPSL uses a mechanical system, literally large, roughly 1 meter in diameter, rotating screws that store energy in the form of rotational momentum. Now, think of them as big flywheels spinning very quickly. Now, these screws are magnetically coupled to a launch sled carrying the rocket, but the pitch of these rotating screws progresses along the track. Now, the magic is in that variable pitch. Now, at the start of the track, the pitch of the screws is shallow, but as the sled speeds up, the pitch gradually steepens, feeding more and more velocity while maintaining around 8 Gs of acceleration until the spacecraft is absolutely flying along at several kilometers a second. The key here is you're not trying to generate gigawatts of power in the moment. You're just transferring kinetic energy you've already stored into the spacecraft. This works sort of like flywheel energy storage or a flywheel battery. Now, in these systems, you slowly spin up a heavy flywheel over time, storing energy as kinetic motion. Now, later, that energy can be released very quickly without needing huge capacitor banks or giant power surges from the grid. Now, the big difference between a flywheel battery and VPSL is that a flywheel battery, once spun up, then converts its kinetic energy into electrical energy, whereas VPSL uses momentum transfer to simply transfer that kinetic energy directly into the spacecraft. Because there's no energy conversion taking place, only transfer, this system is far more efficient. This is an absolute game changer because it sidesteps the cube of velocity problem that has killed traditional mass driver designs. In engineering terms, this means the cost of the system scales with velocity squared instead of velocity cubed. Now, that is a huge difference. A squared curve still rises fast, but it's nothing like the exponential cliff of a cubed curve. Now, suddenly, pushing towards interplanetary or Earth escape velocities isn't financially unfeasible. And compared to a traditional rocket, which suffers from the tyranny of the rocket equation, the VPSL scales far more gracefully. Instead of chasing a death spiral, you're just storing and releasing more rotational energy, making the economics dramatically more forgiving. And because the energy input is spread out over hours instead of seconds, you can use normal grid power, even renewables, without the need for dedicated multi-gigawatt power plants just to launch a rocket. So what does this actually look like in practice? Well, imagine a several kilometre long vacuum tube built along the ground or under the ocean and then either up the side of a mountain or suspended in the air by drones. Now, inside, a sled cradles the spacecraft. Along the tube, large variable pitch screws spin in sync, their motion magnetically gripping the sled. No physical contact, no wear and tear on the rails. Now, the sled begins to move, slowly at first, then faster and faster until it bursts out the tube's far end at blistering speed. Now, at that point, the rocket can ignite its engines, already halfway to space, having skipped the most energy-hungry part of the climb. Now, to put that in perspective, the Saturn V had a launch mass of about 2,970 tonnes. By the time it reached the same altitude a VPSL could provide purely through kinetic launch, it already burned through roughly 1,500 tonnes of propellant. That's over 50% of its entire launch mass just to claw its way through the lower atmosphere. Now, VPSL gets you to that point without using a single drop of fuel. Actually, it gets you far better than that because VPSL gets you up to interplanetary speeds, where the Saturn V's first and second stage only boosted the stack to slightly less than LEO. Now, depending on the payload, the system can be built for different acceleration profiles. Now, for delicate payloads or human passengers, the pitch can be adjusted so the acceleration is gentler, stretching over a longer track. For bulk cargo or unmanned probes, you can really crank it up to high G acceleration to keep the infrastructure smaller. To put this into context, Phil and Alistair's cost modelling for a human-rated VPSL able to launch a roughly 28-tonne spacecraft at 11.1 kilometres a second, which is Mars transfer velocity, that comes in at around $32 billion in capital cost. Now, that's a lot, but in mega project terms, which this very much would be, it's actually really quite cheap. Now, the Artemis program, for instance, is expected to cost $93 billion through 2025, and they've flown once. Now, for launches to Mars, for instance, the cost per kilo would be as low as $3,858, assuming 560 launches over the life of the system. That's cheaper than all current low orbit missions, and we're talking about payloads to deep space. Now let's circle back to those roadblocks that have kept launch assist systems stuck on the nice idea, shame about the reality pile for decades. Now, first up is instantaneous power demands. Now, with older systems, traditional electromagnetic launchers need to dump enormous amounts of electrical energy into the track in just a few seconds. Think 10:04 p.m. Hill Valley Clock Tower lightning strike levels of power, sustained over kilometres. That's not only prohibitively expensive, it quickly becomes a bit of a nightmare to build, maintain, and feed with electricity. You would need literal farms of pulsed power sources like capacitors and supercapacitors.
As a bit more of a physical example, we had these batteries installed at my home yesterday. They just charge up by the solar and they can power our house. Now the two stacks are 25 kilowatt hours each, so it's a 50 kilowatt hour system. Now how many of this 50 kilowatt hour system would you need to launch a 28-ton spacecraft into orbit? 4,700 of this combined system. Now it's actually far worse than that, because lithium batteries aren't able to discharge at anywhere near a fast enough rate to operate a mass driver. So you'd need to use capacitors and supercapacitors. The problem with that is capacitors and supercapacitors aren't anywhere near as energy dense for the same physical size. So take 4,700 of this and times that by another 20 to 50 to equal the amount of power that you would need to operate a mass driver. And even that is the ideal kinetic energy requirement. With real world losses, it's going to be even more than that again.
And then there's the energy recovery, something that is very difficult for a railgun to pull off. Now, you're only realistically going to be able to recover a small amount of the energy used in a railgun. In my research, I was able to find a pretty wide variation of energy recovery figures for railguns, but none of them were higher than 50% in an absolutely ideal theoretical scenario. In real life, you're looking closer to somewhere between 10 and 30%, and even that's optimistic. Basically, with railguns, there's a large, irrecoverable loss of energy. Now, with the VPSL, instead of pulling monster power surges from the grid in real time, VPSL acts sort of like a rechargeable battery. Now, you feed it energy slowly over hours, spinning up those screws, and then at launch, all that stored rotational energy gets transferred mechanically. Think of it like a circus performer on a seesaw board. Now, one performer climbs the tower, slowly storing up potential energy. Then when they jump off and land on the board quickly transfers that energy to launch the other performer into the air. That's essentially what VPSL does, except instead of a single jolt, the screws give the launch sled a smooth, continuous transfer of energy along the entire track. Then when it comes to the energy recovery, when you've finished with the day's launches, you can simply convert the kinetic energy of the screws back into electrical energy through the electric motors used to spin them up. This works pretty much the same way as regenerative braking in an electric car. Now, electric motor generators generally have an energy recovery efficiency of around 80%, far better than a railgun. Now, problem number 2 is wear and tear. Now, the problem with railguns is a lot of power needs to go through the rail armature contact, and the arcing tends to damage the rails. Now, there's also a lot of magnetic force on the rails that can distort them and make them useless for the next run. Another issue is that the current tends to short through the projectile's plasma wake. Now with the VPSL, the spacecraft never touches the screws. The magnetic coupling means the sled is magnetically held in the air relative to the rotating machinery, similar to a maglev train. No friction, no sparks, and no rail erosion. Because there's no electrical power travelling through the rails and no air inside the tube, there's no risk of a plasma wake short-circuiting electronics. Now, problem number 3 is scaling cost with velocity. Now, with railguns, the faster you want to go, the more powered stages you need. Because each stage needs to be more powerful than the last, the cost starts to get out of control pretty quickly. And this is the dreaded velocity cubed cost curve. Now, push for orbital or interplanetary speeds and you're staring at a budget death spiral. Admittedly, if you push traditional mass drivers to Mars transfer velocity, it becomes more like a tie with rockets because of the way these systems scale, but this doesn't really gain us any advantage here. Now with the VPSL, mechanical energy transfer doesn't require adding more and more power electronics into each additional segment of the launch system. The screws keep spinning, and acceleration is just a matter of adjusting pitch. Now this changes the cost curve from velocity cubed to velocity squared. Far from a free lunch, but still orders of magnitude better for high speeds. Problem number 4 is marginal gains. Now, many past concepts, particularly ones discussed by aforementioned YouTube creators, offered only a small boost in speed to a rocket that was already very large and heavy, maybe shaving off a few hundred meters a second of rocket burn. Now, because these ideas are trying to give the entire rocket a boost, the infrastructure also needs to be really large and heavy, and that's not exactly an attractive option compared to just increasing the size of the fuel tank and slapping on a couple additional engines. Now, the VPSL, on the other hand, only accelerates the rocket's payload and a tiny amount of extra propellant on the order of about 1% of a Mars-bound rocket on the pad. The infrastructure doesn't need to boost the huge mass of an entire rocket because, at scale, the infrastructure replaces 99% of the rocket. Basically, there's absolutely no reason to launch a whole conventional rocket with a mass driver. You simply don't need all the additional weight and complexity. The VPSL infrastructure does the work instead, so it can shed 99% of the rocket's mass. Now, the spacecraft does still need a rocket engine to land on Mars, or wherever you're going. Now, that same rocket engine is also used to offset air friction during atmospheric exit. Now, it consumes around 2,300 kilos of propellant to maintain the spacecraft's speed through atmospheric exit in order to send 25,000 kilos to Mars. There's obviously a fair bit of drag created by our atmosphere. Returning to the Saturn V comparison from earlier, it sent about 45,000 kilos to the moon, but it started out being 2.97 million kilos on the pad. So VPSL requires just 0.14% of the propellant of a scale to match Apollo Saturn V launch. That's 700 times less propellant. Now, the result is huge cost savings per launch and far more mass delivered to orbit and beyond. Problem number 5 is human rating potential. Now, with traditional mass drivers, engineers have come up with some other ways to avoid that dreaded velocity cubed cost problem. Now, for instance, railguns developed for the US Navy avoid this by massively increasing the acceleration to make the gun barrel much shorter. Now, this avoids the need to replicate the pulsed power hardware again and again down the length of the launcher, which is what we discussed earlier with the system needing to be more and more powerful down the length of the launcher. Now, humans, however, very much cannot handle tens of thousands of Gs. This would turn you into soup. Now, spin launch, for example, avoids skyrocketing costs by using an electric motor. Now, by spinning instead of going in a straight line, the magnets that accelerate the payload are reused each time the arm rotates, instead of being replicated again and again in the way they would in a linear motor, essentially like a long track style driver. Now, this strategy, unfortunately, also makes it impossible to human rate the system because it leads to enormous centrifugal forces, tens of thousands of Gs, something that even most non-human payloads just can't survive. Now, VPSL, on the other hand, avoids the velocity cubed cost problem by transferring momentum on the fly instead of converting electricity into kinetic energy on the fly. Now, this solution is ingenious because it doesn't come at the expense of human rating potential. Acceleration can be gentle or aggressive depending on your design goals for the system. Now, it's the first proposed system that doesn't cost an arm and a leg and can launch passengers without turning them into pancake batter. When you line it all up, the big takeaway is that VPSL doesn't just improve on old concepts, it removes the exact things that made them uneconomical and impractical in the first place. Let's take a better look at the numbers and a little more context so we can hopefully make this make a bit more sense. Now, the VPSL system is implemented as a digital twin with over 27,000 lines of code. Now, if you're one of the clever people who hears digital twin and immediately knows what I'm talking about, congratulations, you know more than I did before I read this paper. Now, for the rest of us though, think of a digital twin sort of like a really advanced flight simulator for the launcher. In more technically accurate terms, it's not just a simple simulation, it's a detailed dynamic replica of the system's physical, mechanical, and electrical behavior. Basically, the digital twin allows us to simulate the VPSL system in detail. The digital twin includes a detailed cost model, which calculates the fully considered cost of placing payload on the surface of Mars. Now, for the VPSL system, this cost comes out to just $3,858 per kilo. This is wildly more cost effective when you realize JPL has many years of experience sending landers and rovers to Mars, and it still costs them more than $2.5 million per kilo to the Martian surface. This makes VPSL 660 times cheaper than traditional rockets at delivering usable payload to the Martian surface. Very, very rarely in the engineering world do you come across an innovation that makes something 100 times more efficient, let alone 6.5 times that. It cannot be overstated how much of an improvement this is. Now, even still, let's scale it down to something a little more common and familiar, like low Earth orbit. Now, the orbital velocity required to maintain LEO is 7.8 kilometers per second, compared to 11.1 kilometers per second to get to Mars transfer velocity. Now, I do need to mention, even though 11.1 kilometers per second, Mars transfer velocity, is only about 30% faster than 7.8 kilometers per second, velocity required for LEO, it actually requires a little more than double the kinetic energy to achieve, because kinetic energy scales with the square of velocity, not velocity itself. Or, to put it simply, at these speeds, a small increase in velocity means a huge increase in energy. Now, if we use Falcon 9 as an example, being that it's arguably the most cost-effective current method to LEO, it currently costs between $5,000 and $10,000 to put 1 kilo into LEO. So at $3,800 per kilo, the VPSL system is significantly cheaper to put 1 kilo of payload on the surface of Mars, which is 55 million kilometers away, than it is for a Falcon 9 to put 1 kilo into LEO, which is just 400 kilometers away. Think about that for a minute. VPSL is cheaper to Mars than Falcon 9 is to low Earth orbit. Now, before some of you start furiously typing away in the comments saying that the cost per kilo to orbit number I've quoted for Falcon 9 is wrong, there are a bunch of numbers on this floating around the internet which are just simply outdated or plain wrong. The number range I've used here is based on figures directly from SpaceX and NASA's website. I am not a SpaceX or Falcon 9 hater by any stretch of the imagination. I just want to use the most correct information available. So if you still think I'm wrong, that's okay. Send SpaceX an email and tell them they're wrong, because these are their numbers, not mine. Now, why does all this matter? Now, the thing about rockets is that every extra kilogram of payload means more fuel. And that extra fuel needs more fuel to carry it, and then bigger tanks to hold it all. And at some point, you're going to need more engines to provide the additional thrust to lift all that extra mass, which means more fuel again. This is the tyranny of the rocket equation, and it's why rocket costs balloon so fast as delta V increases. VPSL, it just doesn't play that game. Adding more velocity just means increasing the length of the launcher. And that's a curve that scales gently, or scales with velocity squared to be technically correct, not velocity cubed, which is exponential. And because VPSL is infrastructure, not expendable hardware, costs improve the more you use it. Now, the first few launches, they're going to be expensive, but the 1,000th, almost entirely profit. Imagine a future where a VPSL system quickly and efficiently sends cargo to the Moon, Mars, Venus, possibly even orbit daily. Fuel depots, satellites, space station modules, even deep space probes, all accelerated to the edge of space before ever lighting a single proverbial candle. From there, rockets become just one piece of the puzzle, not the whole solution. And that could be the moment we really start building a true space economy with the same reliability and routine as today's shipping ports and airports. Now, I'm just a communicator. I am certainly not an expert in the field, and I would not purport to be. So when I came across this idea, I obviously had a ton of questions. So I sat down with Phil Swan, one of the people behind this research and one of the authors of this paper, to get some answers. Well, hi, Phil. Thanks so much for agreeing to talk to us. Look, we've obviously been talking a little bit in the background, but for the audience at home, why don't you sort of introduce yourself a little bit, what you do for a living, and sort of how you've ended up with coming up with this idea and this paper.
So my name is Phil Swan. I am the lead principal engineer at the Atlantis Project. The Atlantis Project is an organization that's exploring the territory between what I would call conventional wisdom and everything that's feasible from an economics, material science, engineering, and physics perspective.
So I've just given my sort of best shot at explaining VPSL. But coming from you, if you were sort of explaining this to just a regular person, at a barbecue or a dinner party or something, how would you explain VPSL in the simplest possible terms?
Yeah, so I describe VPSL as a technology that reduces the cost of us sending people and supplies to a destination such as the moon and Mars.
How's that different to a rocket, and why would this system be better than using the rockets that we've been using for decades?
Yeah, so rockets are great for getting into low Earth orbit. They cost these days around $6,000 a kilogram to send something to low Earth orbit at the best. If you go into the ISS, it's more like $8,000 a kilogram. But if you want to go to the moon, which only requires about 50% more delta V, then it costs about $1 million a kilogram. If you want to go to Mars, it's maybe $1.5 million a kilogram. And if you want to go to Mars and come back, then you're talking like $8 to $11 billion a kilogram based on the cost of the Mars sample return mission, for example. The cost doesn't go up linearly, it goes up exponentially. And so it's going from $6,000 to $1 million to $10 billion. That's what exponential cost growth is. And so rockets are fighting some realities of physics and economics that are very hard to beat. So when we want to focus on those destinations, we really need to take a step back and think about, can we beat the economics of rockets? Or do we need to come up with a different approach?
I think that's probably really prudent, particularly at the moment. Like, we're seeing some of NASA's more interesting and honestly exciting missions, like you mentioned, the Mars sample return, being cancelled. And it's, you can get into the politics of it, which I don't want to, but honestly, it probably just comes down to cost, because $10 billion is an astronomical amount of money to get, what is it, like 100 grams of dirt back from Mars. It's being able to reduce the cost, especially, getting away from that exponential cost curve, is even just from a science perspective, is going to make such a drastic difference.
Yeah. And if you look at the people who have proposed better ways of getting to Mars and back, like Robert Zubrin's Mars Direct plan, for example, in his plan, they take a little bit of hydrogen with them, some fuel, but then they convert that into much weightier fuel, which is methane and oxygen, using the Sabatier process on Mars. So they have infrastructure on Mars that will convert this little bit of hydrogen and the atmosphere of Mars into fuel they can use to get back. So that's an infrastructure-based approach, which does change the economics of spaceflight to Mars. And we need more infrastructure-based approaches than just that one. But it's a good example of one.
So in the paper, you talk quite a lot about Mars transfer velocity and using VPSL specifically for interplanetary transport. But just sort of on a wider scale, do you see VPSL sort of potentially replacing traditional rockets?
Yeah, largely. To use the term replacing is tricky because you still need rockets a little bit. In the VPSL, we use the rocket to help the vehicle exit the atmosphere. It's needed for steering, and it's needed for fighting the air resistance on the way out. It's also needed to land on Mars. Like, we don't have anything on Mars that can catch a spacecraft, so you need a rocket for that. So you can't get rid of the rocket entirely. But what you're really trying to do is you're trying to get rid of the cost associated with a rocket. And that cost starts out right on the launch pad today. Like, there's many rocket engines at the bottom of the rocket, and a lot of engineering goes into making them as light as possible, as powerful as possible, making sure that the margins are razor thin, and yet the spacecraft won't shake itself apart and blow up on the way up into space. That takes a lot of energy, a lot of work, and a lot of money.
With this system, the spacecraft's going to be exiting the tube inside the atmosphere at something like 11 or 11.1 kilometers a second, which is pretty quick to hit the air. Obviously, a spacecraft coming back from LEO, like the Crew Dragon, they're only doing 7.8 kilometers a second or something like that, and they're coming in from the thinnest part of the atmosphere into the thickest. This is going to be hitting one of the thickest parts of the atmosphere at that full 11.1 kilometers a second. Is that heat load, or potential plasma wave forming on the front of the spacecraft, is that sort of a potential issue, or do you have a sort of workaround for that? Do you want to sort of go into that a little bit?
Yeah, I think that's a really interesting question, because we have been looking at this question of how deep into the atmosphere is too deep for starting your transit, we call it endoatmospheric transit out of the atmosphere. The first thing to consider is like a spacecraft coming back from the moon, for example, also hits Earth's atmosphere at around 11 kilometers a second. So it's a speed that we have some familiarity with. It's much harder to come back from those higher interplanetary destinations because you're coming back in faster. But what's really important to understand is that the vehicle is, when it's coming back, is trying to convert all of its kinetic energy into heat. Now, if it converted all its kinetic energy into its own heat, that would be like probably 10 times more than it would need to vaporize itself. There's a lot of kinetic energy in a spacecraft that's coming back from another planet. So what the spacecraft has to do is it has to try to convert that energy into the heat of the air around itself. And so to do that, they usually use a blunt body heat shield, which sort of keeps the shock front at a certain distance offset from the spacecraft itself. And so there's less transfer of heat from the hot air that's in that shock front, or bow shock it's called. The bow shock has a very hot layer of air in it, and that air is further away from the spacecraft. And so it sort of goes around the spacecraft and ends up in the air, in the atmosphere. So that's necessary because you're trying to keep the spacecraft from getting hot. And you want to get all that energy converted into heat. When you're leaving the atmosphere, you have a different problem. You're trying not to convert the kinetic energy into heat. You're trying to preserve as much kinetic energy as possible. And since you don't want to convert your kinetic energy into heat, you don't need to have a blunt spacecraft. So what you really do is you have a very pointy spacecraft. It's designed to kind of get through the atmosphere really quick, so that the integral of all that heating, like the total amount of heating, is actually still quite low because you're in the atmosphere for a much shorter period of time. You're only going through the atmosphere for maybe 8 or 10 seconds before you're up at the altitude of where it's no longer a problem. Like you're up at 100 kilometers already.
Yeah, so it's basically like the opposite of a re-entry, where a re-entry, the heat is kind of a feature, not a bug. You're trying to convert your kinetic energy into heat deliberately. So
Right.
I guess what you're saying is, with, say, VPSL, where you're trying to get to space, it's actually not that hard to get around the heat issue, because it's not really an issue with re-entry. It's a deliberate choice. Whereas this, you're deliberately trying to do the opposite.
Yeah, you're not trying to heat your spacecraft, and you're not trying to slow it down. So you don't have to treat heat the same way that you do on a re-entry system.
Now, you mentioned obviously the craft is still going to need a rocket motor to compensate for some of the atmospheric drag as it exits the tube. I did have a couple of questions around this. The first one is, with that rocket motor, do you need to fire it while the craft is still actively in the atmosphere, or can you fire it once it gets to space to sort of replace that velocity? Because obviously the last thing you want to do is fire a rocket motor in this super expensive, super delicate vacuum tube. And most, say, turbo pump fed rocket engines take a couple of seconds to start up. You're only in the atmosphere for 10 seconds. So it's almost like you'd need to start the rocket motor up whilst it was still in the tube. You sort of talk about, whether it needs to be fired in the atmosphere, or can you just replace that velocity once you're already in space and you're well away from the tube?
Yeah. So honestly, it makes our math a lot easier if we fire it up the very moment it hits the atmosphere and use it to compensate for the atmospheric drag. So the models we use are basically saying that the rocket thrust is equal to the atmospheric drag exactly. So then the vehicle just continues on basically a ballistic trajectory off into space. Now, if we change the math and said, let's not fire the rocket engine right away, let's have atmospheric drag slow down the craft and then fire it later and accelerate again, I think that would still work. We just haven't explored that particular set of engineering trades at this point, because it just makes the modeling more difficult.
On that note, what do you think sort of the most appropriate rocket engine to use for something like this would be? Because, you could perhaps stage it. You could have one rocket motor that you use, to replace that atmospheric drag, and then have a secondary motor for landing on Mars or something like that. My thinking would be, keep it simple and have one motor that does both. Is that sort of that you're thinking around this, or do you have, is there a better way of doing it? What sort of engine do you think would be?
Yeah, I totally agree with that idea. Like, I don't see the point of having two different rocket engines or two different stages. But it's kind of an economy to have the same rocket engine that you need to land on Mars be used to get out of Earth's atmosphere. So that that's just, to me, a good engineering trade. The best type of rocket engine, if we had to decide right now today, it would probably be a hypergolic engine with bipropellant. So that's a very reliable form of engine, starts up every time. And they used it all throughout the Apollo program when they were beyond Earth's orbit. So they didn't want to land on the moon and then have a finicky engine not bring them back. So they use hypergolic engines for that. And they basically 2 valves, fuel goes in, rocket starts, guaranteed. But they have already started exploring the idea of using hydrolox engines in deep space. I think there's one company that's already done it. It was traveling to the moon. I forget the name of the company, but it was one of the recent missions, one of the recent commercial missions to the moon. So that was pushing the bounds of technology. But that's a probe. Maybe they can afford some risk. I like to believe that by the time we get to this point where we're using infrastructure to go to the moon and Mars, that we could make an engine that starts up very reliably and uses propellants such as hydrolox that have a very good ISP or a very good exhaust velocity and are made for very efficient engines.
I think when we spoke about it earlier, I mentioned to you, perhaps even using something like Rocket Lab's Rutherford, being that it's an electrically, that the pumps are electrically driven, so it's a much simpler, probably more reliable system when you're trying to start up in space. And so your onboard battery, because you're only, transiting the atmosphere for 10 seconds, you can get away with probably a pretty small battery, which you can then just recharge. I think you actually mentioned you could just recharge it with solar panels on the way to the moon or Mars, and probably still get a pretty good ISP. You could use a hydrolox system, perhaps. So you're still getting that good ISP, but you've simplified the engine significantly.
Yeah, I thought that was a brilliant idea. I didn't think of it until you came up with it. And I think that's a really good idea. It makes a lot of sense in this particular application to use electrically fed engines. And I think Rocket Lab has pushed that technology and shown that it works. So it's something we can say is a high TRL level already. So yeah, that's a great selection.
Look, thanks so much for joining us and sort of shedding a bit more light on this. I know I've gotten a lot out of talking to you, but both today and the other times that we've talked. And I think the audience definitely will have gotten quite a lot of beneficial insight out of actually hearing it from you, not just from me, because I'm obviously not an expert. I'm not an engineer. So it's been really good to have you on and hear a bit more about it and ask you some questions. So thank you.
Yeah, and thank you for suggesting the Rutherford engine idea from Rocket Lab. I think that's really good. That's the kind of thing I want to get from experts, and I got it from you. It's great.
All righty. Thanks, Phil.
For decades, the dream of launching spacecraft from the ground without burning through mountains of fuel has felt like something just over the horizon. Sort of like nuclear fusion power plants. The physics was fine, the engineering was possible, but the economics were absolutely brutal. That's why so many smart people, including voices I deeply respect, have concluded that many of the ideas in this category, the more traditional mass drivers, just aren't worth it. But technology doesn't stand still. The variable pitch screw launch is proof that sometimes the barriers that seem permanent are just barriers to that version of the idea, not the idea itself. By changing the way we store and deliver energy, VPSL sidesteps that cube of velocity curse, flattens the power demands, and avoids the mechanical destruction that doomed earlier attempts. It's not just another railgun concept. It's a ground-based launch system that can realistically compete, if not win out on cost. Yes, VPSL is a mega project. Yes, it would cost billions, but so did every piece of infrastructure that changed the world, from the railroads that opened continents to the undersea cables that connected them. The next giant leap for space travel might not be a bigger rocket. It might be a track, curving up the side of a mountain, quietly storing energy until it's time to send the next payload or the next crew on their way to orbit, or even the new world. Now, if you liked or found this video interesting, go ahead and click on one of my other videos that should be popping up on the screen in a minute. And if you like those and want to see more, I invite you to go ahead and hit the sub button. I come out with new videos every 2 weeks. Now, if you'd like to hear more from Phil Swan or have some questions about the VPSL system, let me know in the comments. I would honestly love to do a follow-up interview to talk more about it and answer some of the questions that you guys may have. And if you'd like to see the full interview, please let me know. Maybe I can put a special link up or something like that. Now, this video was really time-consuming and complex to make, so if you want to support the channel even further, I do now have a merch store with some cool space-related gear. There's some classics in there like the ROP Pluto and Project Orion range, but there's also some others in there which I designed myself. My personal favorite is the nuclear fusion range, which has a couple of hydrogen atoms that have been cable tied together. The not unsymmetrical dimethylhydrazine mug is also a personal favorite of mine. You get yourself some cool stuff, you support the channel, everyone wins. Anyway, thanks for watching, have an awesome week, and I'll see you next time.